Welcome everybody. Let's talk about this question 8 from our vector valued functions practice. I want to show you how you can use vectors to work your way through a problem like this. So here's the situation that we've got. We got water flowing down a river. So let me just give ourselves the river. We're going to just give ourselves sort of the most basic straight river here. You got water flowing down a river. The way that fluid flows typically is it's faster in the middle, slower on the outside, so you got to deal with that. And so we're going to come up with a model for this, but we get this river flowing north, and we're going to have a point here. We've got 40 meters across. We get this straight section of river, and we've got a formula that's going to tell us how fast the water is flowing. And so we got this function that will tell us the speed, and it's different in the middle than on the outside. So really I should actually draw these a little bit different because the speed of the river is big in the middle and then smaller as you get to the outside. And of course it is a vector here that you can go through. And what we'd like to figure out is some information about where we end up. And so let's work our way through this. So what is that going to look like for us? If we leave this point P here on the west bank and we're going to head straight across. Well, what's going to happen actually is the boat is going to start to travel with the current. So the boat is actually going to go sort of upwards somewhere and end up at some point Q. And our task is to figure out where this point Q is. Now, we're going to take advantage of vectors to do it, but there's sort of a tricky thing that here's what we can do. We can actually work out, at least in part, the velocity of the boat. Because here's what we know. We know the boat is moving at 5 meters per second. We were told that. And the boat is moving straight perpendicular to the west bank. That means the boat is actually trying to move straight east. And so the boat is moving 5 meters per second east. And it's moving something north. But how much? It depends on the x-coordinate. We have a whole formula here. It's going to be 3 over 400x 40 minus x. This is so that in the middle this is 3 meters per second and then smaller as you get to either end. It's got a symmetry in it. If you know the x-coordinate of the position, then you can figure out this velocity. But that's sort of circular reasoning here. So you have to be careful about this because what we just said is in order to know the velocity, you need to know the position. But guess what? In order to know the position, don't we need to know the velocity? Isn't that how we're going to find the position? You find the velocity, you anti-differentiate to find the position. And yes, but we get around that as follows. If you focus just on the x-coordinate, we can find just the x-coordinate. And so what we're going to say is that the velocity is 5, question mark. We don't know. So r of t will be the integral of that. So it's the integral of 5 dt, the integral of we don't know. So we can't compute that second one plus some constant vector here. But we can solve this. We can work out that this is 5t, an integral of question mark dt plus c. And we know that when t equals 0, we're just going to call that starting point 0, 0. We're going to put that as our origin of our system. This implies that c is going to equal 0, we don't know still, because we've figured out nothing about the y-coordinate, not the tiniest little thing. But we have worked out the x-coordinate. The x-coordinate of the boat is 5t. And here's what that lets us do. It lets us come back into this formula, and now we know where the boat is. We don't have to use x. We know that x is 5t. So we can actually work out that this is 3 over 400, 5t, 40 minus 5t. That's our y-coordinate of the velocity. This is how fast the water is moving, where the boat is. is what we get. And so we've done part A here. We found a formula for the x coordinate of the boat, and that allows us to start getting access to the y coordinate, because the x coordinate of the boat, where you are as you move across, tells you what your x value is to plug into the velocity. When x equals 5t, we can find the y velocity, how fast the boat is moving downstream. And so we get to write down our whole velocity function. 5, we already knew that. But then we have the y component that looks like this. And if we grab this velocity, now we don't need so much more of this page. We have encapsulated the motion of the boat into this one lovely formula right here. So let's move forward a slide. We'll write down our whole velocity. And now we can find our integral. So r of t is going to be the antiderivative of both of these. 5 dt, an integral 3 over 400 times 5t times 40 minus 5t dt. And we can do these integrals relatively easily, especially if you pull out this 15 over 400 and you distribute the t. We're going to get a 40t minus 5t squared. What I've done here is I've multiplied the t into here. I've taken all the rest that's a constant and I've dragged it outside of the integral. I still have a dt. And so now we're firmly just in the integral phase. I've actually done my first integral. We're going to get a plus vector c, of course. 15 over 400, 20t squared minus 5/3 t cubed plus c. The initial condition, t equals 0 and r equals 0, the 0 vector, means in this case, when you plug in t equals 0, you're going to get 0 for the r on the left-hand side. You're going to get 0 for this big vector. You're going to deduce that c actually is the 0 vector, and so we can ignore it. Not ignore it, but not write it anymore. And I'm just going to do a little bit of distribution here. This is going to be 3/4 t squared minus, when you do this multiplication, 25 over 400, which is 1 over 8 t cubed. 1 over 16, excuse me. And so now we know exactly where the boat is. What you want to remember is that anytime looking at a formula, you want to be thinking about the formula in two ways. Number one, the precise details. Hey, this formula r of t is 5t for the x component, 3/4, and so on and so forth. The formula itself, but almost more important in terms of how we use it, that this tells us where the boat is, that you plug in a time t and you get an output that's a position. And so that means when you're trying to connect position and time, this is the formula you wanted to use. Okay, let's jump back to the question. We are trying to figure out how long it takes to reach the east bank. Well, the east bank has an x coordinate of 40 meters. So the east bank, we can really phrase this as when is the x coordinate of position 40 meters. Well, guess what? The x coordinate of position is 5t, because we have this sort of dictionary here that you input a time t, you get an output of position. This thing highlighted in yellow is position. We just want the x coordinate to be 40, so t equals 8 seconds. It's going to take us 8 seconds to cross the river. Okay, how do we finish this then? What's our last question? And I'll leave the bonus for you, though I'll say a few words. How far downstream from its starting point does the boat reach the east bank? Well, how far downstream is just what's the y coordinate that we've got going across here, an x-axis. I know the x coordinate of Q, it's 40. I want to figure out the y coordinate. And so we just ask, what's the y coordinate when the x coordinate is 40? In other words, when we're at t equals 8 seconds, what is the y coordinate when we've successfully crossed the bank? When t equals 8, well, the y coordinate is 3/4 t squared, except for we're not going to do t, we're going to do 8 squared, minus 1/16 times 8 cubed. And all you have to do is calculate this value. So you pull out your trusty calculator, you calculate the value, 16 meters. And we've answered the question. Now, in practice, all of these steps A through E really build into just answer E. That the real question here, and actually the source that I took this from, was just question E. How far downstream from its starting point does the boat reach the east bank? Everything else is sort of the thought process that we go through to solve the problem. So that's really what you want to be thinking about, is what is the process? What do we know? We know that we have a constant speed of 5 meters per second. Do we know the direction that's heading? We also know there's vectors about speeds. We know the speed of the water, and the boat is going to be simultaneously the engine's 5 meters per second and the water's velocity, and we can go from there. And so that sort of gets you started. It's also this sort of piecewise bit that you can do the x coordinate first, because with vectors, the x coordinate and the y coordinate, the calculus piece of it doesn't really interact. The description of the problem forces us to do the x first, but the calculus doesn't interact, at least in this case. And that's what makes this a doable problem for us now, as opposed to differential equations, really. Just a quick idea of what would you do to solve F. Now we're going to aim the boat. We're going to actually, instead of going straight across, I'm going to say I got a new point P, and I'm going to try to end up straight across. And so obviously, if the water is going up, I'm going to need to aim down. Right? I'm going to aim down and then hopefully get back to Q. Now it turns out it actually won't end up looking like that. If you get the correct answer and plot it, what it's actually going to look like is this kind of thing. Because at the beginning, you're going to make up some ground going up the river a little bit. That's down on my graph. In the middle of the river, with a course of the river, the speed is bigger, you're going to be sort of losing some ground, and then near to the other side, you're going to make it back up again. But how do you actually work this out? Well, the main thing is you're just going to change this 5. And instead of this 5, you're going to just work out by putting a theta. You're going to break down that 5 into 2 components. How much is horizontally going across the river? That you replace the 5 in. How much vertically is sort of fighting against the current? That's going to go in as an addition onto this y component of our velocity. And so you'll just have 2 components here, a completely different x. You'll have to set up this y component separately. Remember that you start with the x coordinate, you find the vector valued function after you found the first integral, and you can work your way through the process. So I just wanted to record this video because I think it's a neat problem. It's a fun way to think about this. It really is this idea of when you have a function, ask yourself, what is this function calculating? Because we're going to have so many functions. Math has so many functions in it. It's got our position, our velocity, our acceleration. We're going to have curvature functions. We're going to have tangent vector functions, the normal vector function. There's so many functions around. Always, when you're thinking about the function, ask, what does the input represent? Do we know? What does the output represent? Sometimes it's a real world thing. Sometimes it's just, hey, the output here is the output, or the output is the derivative, the direction of that previous output, and so on and so forth. But keeping track of what the function can do for us lets us put that function to work. That's it for today. I will see you in the next video or in class.